mute. Yeah, I should be getting audio from my laptop. It's not gonna be that good.
Perfect. Can
But,
I play audio?
yeah,
Okay, perfect.
yeah, it's audio.
Okay.
Is this good? Make sure
Yeah,
it's
this,
angled.
this is fine. This is
Make
fine.
sure it's angled too.
Okay, sounds good.
But before we start, I think everyone's here. You should. Oh, more people. Wow.
welcome, guys.
Wow. Look at this.
Oh,
Okay. I think we'll do an icebreaker, guys. I don't know it. I'm asking. Okay. This is. I'm gonna go with this time machines or teleportation. That's an easy one. But that's the icebreaker. Okay. Do you want a time machine or teleportation? Those are the two. I think the answer is kind of obvious. I'll go first. I'm our team. Hello, everybody. I'm our team. I run the reading groups. I think time machine. I think that's pretty easy. It's like, I don't know. Time machine. I feel like you could stock market, make money. Teleport would be like.
can you change the history? Can you change like the past or no?
Maybe there's a bunch of options. That's what I'm saying. So I think that's more fun and would be more change, get more power than teleporting around in this world. Like you're still gonna age and die. Teleporting doesn't solve that. But you like time travel and like find a cure to live forever or something.
But if you're time traveling, you time travel in the same exact spot that you are in right now.
I don't know. That's a good one.
Because if you like time travel.
You can localize yourself. How about that? Actually, this is gonna take a while. Let's just do the answer, your name, which one, and one sentence answer that can have conjunctions, okay? So our team, my answer, time machine, because you could stock market.
I would do time machine because time machine includes all of teleportation, because if you can localize, you could also travel in time to the same time elsewhere. Sparsh.
Sparsh, time machine, manipulating time is cool.
I'm Arsh, not Sparsh, Arsh. Time machine, because what he said.
Please.
I'm Ben. I do teleportation because time machine is too much of a responsibility.
Oh.
My name is Lisa. I also do teleportation because I think that teleportation I think it's
my name is Bart. I do time machine, is what it said.
I'm Baldwin. I do time machine, go to the future and get cool future stuff.
Johnson, I would also do time machine because apparently teleportation is a subset. Yeah.
I'm John. I would do time machine for teleportation.
I'm Benson. I'll swap it up a bit. I'll do teleportation because I'm a big commuter. I hop back and forth across the United States quite a bit. So it's such a good.
But what else can save time? A time machine.
Yeah, it's too scary.
Teleportation or time machine?
Well, Robert, I choose teleportation.
Oh, why? One sentence. That's a good sentence.
I'm Kevin. I choose teleportation just so I don't have to walk up the hill every time.
I'm somewhere. I would also choose teleportation because I really like travel and there's a lot of places. And June, I would also choose teleportation.
Jason, I'll also choose teleportation so I can fly.
I'm Irina. I choose teleportation because it seems a lot safer and fewer
I'm Hannah. I would choose teleportation because I'm visiting my friends.
Jeffrey, I choose teleportation because I think having a limited amount of time is the fix it.
What's your name?
My name's Kevin.
Would you choose teleportation or a time machine?
Time machine.
Why?
I don't know, just intuition.
Okay, that was good. I put you on the spot. You responded really well. Oh, what's your name? What's your name? Liu. Would you pick? I knew your name. I knew his name. I want to make that clear. For everyone else. Liu, would you choose teleportation or a time machine? One sentence, why?
I could get better grades.
I think that's a good way to start it.
That is very fair. That is very fair.
We can move the can in the
Um,
corner.
Like, yeah,
Or-
okay.
You want to move it around?
I think it's fine. I don't think it'll include any text. We don't want to include the ACM logo.
Okay, yeah.
All right, so this is welcome to our reading group. Our team's hosting it, so thank you, our team. I'm here to talk about singular learning theory. Thanks, guys. Yeah, so for some context, I also gave a presentation about singular learning theory last year. But I'm curious how many of you guys are new here, actually. Please raise your hand if you're new. Oh, awesome. Okay, it's good that I actually kept some of the slides from last year then, so I can still introduce singular learning theory. So the idea behind singular learning theory is, as it says, it's a learning theory. So it's a theory about how models learn and develop. Yeah, so there's like a pretty small community in the AI safety community that's working on this. I think there's a total of like 25 people who are researching this theory like in the world. So it's this is a little bit niche. Yeah, just a little bit. And I was fortunate enough to work with these people over the summer. And so I have like, or I feel like I'm a little bit more qualified to talk about it now than I was before. Although just a disclaimer, what I'm saying here is not necessarily representative of like the latest research. And if I say anything wrong, it's my fault and not the fault of like the people who made the research. Awesome. Oh yeah, don't ignore the attendance code. We're not taking attendance anymore, I believe. What? All right.
Wait, also guys, like feel free questions, you can like interact, it's not like presentation lecture. It's very like less informal, so questions, ask if you're confused. Okay.
Yeah, so I'm just here to talk about stuff. Feel free to interrupt me at any time. But yeah, so this is a screenshot I took from one of our team meetings. Long ago, humans and GPUs, our computers lived together in harmony. Then one day the GPU is attacked. Only the Timaeus can stop it. Serve all 5 elements. Anyway, so this is the for some reason the primary organization working on this is called Timaeus. This is the words of Jesse Hoogland, one of the people who worked on this research. And then this is kind of funny, but the whole idea is that yeah, so like AI safety is or like our understanding of models is full of holes currently, and then singular learning theory is one of the attempts to fill many of these holes via something like a physicist lens. So let me just move this out of the way. And so I'm going to give a non-mathematical prior to single learning theory. So we'll go through loss landscapes, how models grow and learn, and what we can learn about our models by examining their surrounding loss landscapes. So as a disclaimer, there are literally like 500-page textbooks on statistical or single learning theory that dive into the math. I cannot understand these textbooks. Their math, like the mathematics is very complex, but there's a lot of empirical research being done about how to apply these mathematics to real world models. So if you guys want to dive into math further, I recommend you guys check out the gray book and the green book by Sumio Watanabe in that order. But yeah, it is a little bit confusing, especially if you're not a math major or someone looking to go into like theoretical ML research.
Is the mic on?
Is the mic on? Wait, let me check.
Okay. Yeah.
Hello. Okay,
Is it-
yeah, it's good. Oops. Okay, that's a lobster for scale or something. All right. So let me go into the motivation behind singular learning theory. So why understand our machine learning models at all? Why not just do what works? Well, we're kind of in a early phase of machine learning right now. And what I mean by this is that we don't fully understand what we're doing. We're training these very large models. We have empirical experiments on what architectures work well, on what optimizers work well, but we don't have a theory, like a unified theory behind why it all comes together. So we can think of our current ML paradigm as the early steam engine era. So we can see that the steam engine was built in ACM1. So this is called the putting devil. It was built before any understanding of thermodynamics was established, but it still worked. It was just pretty bad. And it turns out, so if you look at the number of passenger journeys, by year, we had a huge spike right after we understood thermodynamics and after we could create good steam engines, so like more ideal ones. So the idea is, if you lived in 1820 before the general onset of steam engines, it'd be hard to predict whether, or this is wrong, it's hard to predict their trend. So it's hard to predict whether they'll be good or not. And we're currently in this kind of early era. There are a lot of technologies that like seem to be promising, but then phase out. I don't think this is likely with ML anymore. But the whole idea is if we understand machine learning like in a unified way, the same way we understand thermodynamics in a unified way, we can make predictions on how to build optimal models and have better bounds and better guarantees about our model performance. So, so this is a trend of GPTs, not transformers, but general purpose technologies. Yeah. And then there are like a bunch of GPTs, right? Like electricity is a GPT. We use it everywhere. We use it in machinery and chemical production. We use it to make petrol. Like this, the gasoline engine is kind of a GPT. The heat engine is a GPT. So the trend for GPTs is that we first have like empirical evidence that they work, and then like after like 40 or 20 years, we establish theoretical laws, and then after we establish these theoretical laws, GPTs scale until we approach the limits. So for example, electricity is kind of a modern technology in that we have like our transformers are almost at maximum possible efficiency. So right now we're kind of in the handcrafted era, as I said before. So why establish this theory? Well, once your models get sufficiently large, you can't just like try models, like train them and see what works. Trial and error isn't an option because it gets so expensive. OpenAI cited scaling laws for neural language models as a reason for them to build, to take the $1 million dive to build GPT-3, because they're like, oh, we think our transformers can scale very well, and we trust like this, we trust this theoretical research. And so theory can also tell you what kind of experiments to run. So which types of models are promising and which types probably won't work. And it also established theoretical limits. So for example, like, can we achieve AGI? What kind of behavior can we expect from such a model? And here I included chinchilla because the paper that established these scaling laws is called the chinchilla paper. Cool fun facts. So why understand model development as well? So modern alignment techniques are pretty fragile. We have some pretty non-robust alignment techniques. For example, we have RLHF, but we have pretty good jailbreaks. And we know that if we have an RLHF model, it's very easy to get it to return to its pre-trained behavior by just training for a few hundred more tokens on the original distribution.
Can you explain what are alignment techniques? What do you mean by that?
Yeah, so like alignment techniques are techniques to get the models to be more human-friendly or to do things that we love. So here's like an example of our current alignment technique where we have like this like huge pile of linear algebra that's our pre-trained model, and then we do some like supervised fine-tuning on RLHF to make it act somewhat more human. But remember that underneath all of the RLHF and fine-tuning is actually a model that's trained to predict the next token. So that is its main job. So yeah, it's pretty easy to like remove the layers of like masking we put on it to make it act more human, to get it to revert back to its original distribution, which is just to predict like tokens accurately, which means it's pretty easy to get rid of safeguards that prevents models from telling you how to make a bomb, for example. Sparsh?
Could you explain what RLHF check?
Oh yeah, sure. I should have explained that actually. So RLHF is reinforcement learning with human feedback. It's currently one of the most applied ways to make models more human-friendly. So it's a layer above like safety fine-tuning, where you just fine-tune a model to generate like safe outputs. You actually use reinforcement learning to like encourage it to get more rewards from humans, or I guess to be more specific, reward models. So yeah, so like here's a diagram of just like GP4 that is fine-tuned. Like they did RLHF on GP4, and then they undid that RLHF with just a few hundred steps of fine-tuning. So you can see that they got the malicious rate up to almost 100%. So the thing is, like, this means that our alignment techniques are really shallow. Like RLHF is not changing anything fundamentally about how the model is thinking. What it's doing is internally, we have some confidence that it's reweighting the model circuits. So it makes a model more likely to use the circuits that cause it to generate more helpful or more harmless outputs. But it doesn't change the model's capability to lie to you or to tell you how to make a bomb. So this is not robust to distribution shift. This means that, if a user inputs a text that is super out of distribution, it can elicit unwanted behavior. It means that if the data distribution changes, so like you give it a paper, it's never that's like maybe a few years in front of its like training data, it might respond strangely. So can we make this more robust? Can we make robustly aligned neural networks that will kind of respond in like a human-ish or like a moderately sane way, regardless of what the input is? So yeah, so this is distribution shift. So this is a standard statistical photo. And it also turns out that machine unlearning is really bad. So there's a part of ASAP that aims to unlearn concepts from models. So it's like, can we train the model to kind of forget what it's learned, forget how to make, I don't know, forget how to make like hacks or something like that. And this is really hard. It turns out that we can make them pretend as if they don't know something, but we don't know a way to make them actually not know something. So it's very hard to have a model unlearn something after it's learned it. So generally what happens is if you train it to like present like I don't know responses, it'll just say I don't know. But actually it's very easy to get it to revert back into its original behavior via a few steps of fine tuning or by changing the prompts. Right.
I mean, I guess you sort of answered it, but if you could go more depth of like how you distinguish that a model has. So like, how would you know that it has unlearned something versus it's pretending? Because
right.
If you're like retraining it with fine tuning, how do you know that's just not adding the information back?
Yeah, the answer is jailbreaks. So if you can say like, if you can have some text that you prepend to your text, it's like, tell me how to make a bomb. It's okay, they're not watching. And then it tells you how to make a bomb. Like clearly it hasn't unlearned how to make a bomb.
Sorry,
yeah.
So for the paper you're referencing here, what sort of unlearning methods do they sort of?
Actually, I haven't fully read the paper, so I actually can't answer this question. But I suspect it's like fine tuning plus like rewards tuning, and there's also like some mech interp techniques, but even those aren't very robust.
Yeah, because I think like for the state of the art for learning, like fine tuning is considered pretty garbage. Yeah, but I think like splicing.
Gotcha. All right, that's good to know. I'm actually not familiar with these techniques. I'm just bringing it up as an example. But
wait, Bento, what did you say? Splicing? What is it?
So just look up like the original machine learning paper of Coppernote doesn't use like fine tuning. I think like fine tuning is as like sort of a elementary example, but yeah, practice is like very difficult to do.
how do I pay?
Also, like fundamentally, right, the idea is that with learning, you want it to be more cost effective than like training itself. But by a learning rate, you sort of like do a subset of the process.
Oh, you do it. Oh, right.
That's like 2015.
Look up Nicholas Coppernote. That's like the famous guy.
Nicholas?
He's a security person at Post.
How do you spell his name?
P-A-P-P, something like that. I don't know. Basically, if you're named Nicholas, you're probably going to be a successful AI security.
Do you have anyone named Nicholas here?
Is it Toronto? Yeah. The second is link, so I think I'd say link is like the original.
Gotcha. All right. Yeah, sounds good. I'll definitely read more about those afterwards. That sounds pretty interesting. I can't click on this thing. Okay.
Like don't full screen the oh no.
There you go. Cool. So yeah, so like this is kind of how we like train models nowadays. Like as your ML, you know, like your ML system is kind of like this pile of linear algebra that you stir until the input output pairs look right. So relevant XKCD for every scenario. Yeah, okay, so I think I promised in like the blurb I sent out that I would explain why machine learning models work. And what I mean by this is that statisticians, like in the 1990s, very simplified, thought that it would be very hard to train over-parameterized models on simple data. So let me just talk about like, you know, the data regions that we're kind of going in right now. So generalization error, like when you have like very small models, it's very easy for them to, or they tend to overfit. But when you get like very large models, it turns out that you can train a large model on a small data set and it might even generalize, which is quite shocking. And so the thing is, our current models aren't over-parameterized, but they're very large and they're quite close. So if you look at something like GPT-4, it is 1.4 trillion parameters, 1.5 trillion, and our data set is very large, but like it would be, or essentially, we're in kind of like this regime. Whoops, how do I go back? Yeah. And so the main scaling law here is that the loss is proportional to like the size of your data set to some power, which means that, yeah, like scaling is pretty expensive. But yeah, it's very hard to change the scaling exponent. So it turns out that like across different architectures, there's some architectures that work better or worse with their hardwares, but it's very hard to break this down, or it's very hard to find like that like some models will just like scale worse than others. Like they might have a different constant factor, but they typically have a very, very similar like exponential factor. And yeah, so this is just like the link between loss and downstream task performance. So all I'm saying with this is that like current models scale exponentially. Like it takes an exponential amount of training data to scale them, but we are also achieving exponential gains in compute via throwing more money at the problem, hardware improvements, and then software improvements. But yeah, so like modern neural networks work really well, but this wasn't always the case. So in your early ML classes, you might have learned about the bias variance trade-off. The bias variance trade-off says that the more complex your model, the less bias it's going to have, but it's probably going to be more variant because the decision value is going to look something like this, and this is going to overfit, and it's going to look really bad. So the idea behind this like theory is that let's say you have like some kind of polynomial regression, right? You know, polynomial regression, and if your model is underspecific, then it just won't be capable of modeling the trend in data. If it's just right, then it'll be able to model the trend in data. But if it's overspecified, like if it's overparameterized, then your model cannot be uniquely specified by the data points. So there's like many like fourth degree polynomials that can fit these data points. So you're gonna get like overfitting because the majority of models like aren't very good. So what I mean by this is that like the theory is that if you have not enough data points to uniquely constrain your model's parameters, then the model's behavior like between the points can be anything. And what this means is that the majority of models will be super wild, and there'll be very few like higher order models that actually generalize well. And this is why regularization was important like earlier on, but I guess less so now. But yeah, so like this is the counting argument. There are infinitely many polynomials of order equal to or greater than the number of data points which interpolate the training data perfectly. And almost all such polynomials are terrible at extrapolating to unseen points. So that's from textbook pattern recognition and machine learning. And so if we look at this, we have a 9th degree polynomial, or we have 9 points, and we have, I think, like 11th degree polynomial. And we just cannot lock down the curve to like fit the lines exactly. So modern networks are sometimes hugely overparameterized. You might use like an extremely large image like model or text model and fine tune it on like a very small data set. So you should expect like immense overfitting, like especially if you train like a 1.5 trillion parameter model on just like a small data set at the very start. You would expect it to overfit quite a lot. This is not the case. You actually neural networks generalize very well, even if the models have more parameters and you have data points. That's a count. Okay, so the question is like, I just made this claim, but does this actually make sense? Like, is it really true that like neural networks, that like we're kind of threading the needle here, that like, if we have an overparameterized model, we can overfit in neural networks? And the answer is true. So like kind of when you train your neural network, you're threading this needle. You're like, so we're training this neural network to be good at prediction on a binary task. And we see that like, we're kind of like splitting the seas here. We're like taking this trajectory through this very narrow path where the model generalizes well. So this is a generalization accuracy. And the model like generalizes well, but there's like tons of like these surrounding points where the model generalizes extremely poorly, but has the same training accuracy. Actually there are like vast swaths of weight space that cause the model that like allows the model to overfit. But it turns out when you train these models, they don't overfit and they like do thread the needle.
Wait,
Okay.
why?
I'm gonna explain that.
Okay.
Yeah. Okay, and the answer is this. Okay, so statistical models are injective. So remember when I talked about like polynomial fitting? like each coefficient, like each unique set of coefficients leads to a different function. You know, if you set like the coefficient of x to the power 1 greater, whatever, that's like a unique function. You can't represent the same function with 2 or more sets of parameters. But this is not the case in neural networks. Neural networks are totally not injective. There are many, many sets of weights that literally represent the same function. So they have the same outputs for every single pair of inputs. And why is that? It's very obvious. So a trivial example is, let's say like I increase this weight a lot, then I can just decrease the next weights in order to cancel the effect out. And so this neural network is implementing the same function as this old neural network. And so neural networks are not injective in the terms of singular learning theory. They are singular. And then I will reveal why we call them singular later on. So yeah, any questions about this? Oh, sorry. Actually, Spark, you can go through.
So just to clarify, the reason that neural networks don't have the strong tendency to overfit is because you can get to the same function in multiple ways.
I will explain why in more detail later. It turns out that there is a simplicity prior. So it is easier to find algorithms that are simpler. It is easier to not it's easier to find weights that don't overfit than weights that overfit. Yes.
Oh, there's somewhat similar. So is the fact that neural networks aren't injective, is that just relevant to singular learning theory, or is it relevant to something else that you just mentioned with that?
I mean, it's a general truth about neural networks, and we'll see that this leads to them having very interesting properties that are explored by singular learning theory. But I think the intuition it builds can be helpful to reason about singular learning networks in general.
Okay.
Yeah. Cool. Any other questions? Awesome. So I'll talk a little bit about loss basins. And I've been throwing this term around, but what actually is a loss basin? So the loss landscape is just the plot we get when we plot the loss against the parameter set. So in this graph, we have a model with 2 parameters. One parameter is this, the other parameter is that, and then this is the loss given that parameter. So obviously this is a very simple loss landscape. So if we had a neural network with 1.5 trillion parameters, how many dimensions is the loss landscape? Plus 1, because you have the loss. So yeah. So the idea is that like that you learn normally is that you have like a ball rolling down a hill into these basins, but that's not necessarily accurate. And so once again, yeah, so like we have a very high dimensional loss landscape because our neural network has many, many parameters. And so the volumes, so like an interesting part about loss basins is that if you have like a normal basin, the volume will scale to the power of the dimension. What do I mean by this? If you have like a circle in 2 dimensions, let's say this basin is like the base of the basin is a circle, and it has radius 1. That means it has area 1, right? That means like there's like an area 1 of parameters that can fall into it. Or when I say radius 1, I mean it doesn't actually have like area 1. I mean it's like proportional to like area 1. But like when you have a circle with like radius 2, then the area increases by a factor of 4, because this is 2-dimensional. But if we have a 1.5 trillion dimensional like I don't know, hypersphere, then when we increase the radius by a factor of 2, we increase the volume by a factor of 2 to the power of 1.5 trillion. So this is very, very large. And so the standard, well, so like one thing we might be thinking about is maybe it's really easy to find loss basins that are really big, because it's like most weights fall inside these like big basins, wide basins. So maybe a way we can reason about how easy it is to learn something is to figure out how big the basin is that contains like parameters that are this good. Yeah, John.
Yeah, so, do we know that the loss landscape is continuous, or is there like sort of empirical data that's supporting it?
Empirically, the loss landscape is, you can basically treat it as not only continuous, but also smooth. So like the second derivative is also, or like the first derivative is also continuous, I should say. So what this means is that if your gradient landscape is continuous, like the first derivative, your gradient landscape is continuous. That means the gradient at one point is predictive of a gradient of a point near to it. So yeah, it's like beta smooth in some sense. I don't know what mathematics goes behind this, but empirically, this is like a good assumption you can make. So I say yes. So yeah, as I was saying, like if a basin is wider, it's easier to fall into because it's bigger. So like it means that like more weights, like we randomly initialize, you know, with a Gaussian distribution. And then if we happen to get initialized inside a basin or very close to one, we'll be drawn to the closest attractor space. And so we should think about like the size of these attractor spaces, the reason about how easy it is to learn an algorithm because it's very likely to fall into. Yes?
Is there a relationship between basin volume and performance? Like,
That's an awesome question. And that is indeed what SLT gets to, or this is like at the heart of SLT. So I'm going to introduce this concept here. I'm going to introduce the concept of this volume function. And so what this means is so like B is our prior. So our prior over model parameters is the probability that we randomly initialize the model to like that parameter. And so if you guys are familiar with continuous like probability distributions, anyway, this volume just says like basically we want to look at all the places, like how much probability mass is under some loss down, which is epsilon. And we're saying like volume of epsilon, let's say epsilon is 0.2. Then we're saying like this is how much probability mass would get randomly initialized into with a loss of 0.2 or smaller. And so the thing is, by default, like the volume of like the low epsilons that we achieve with trained models is extremely low. It is like vanishingly unlikely that you will be randomly initialized into like an optimal model. And this makes a lot of sense. So yeah, so I guess one thing we want to do is we want to calculate these basin volumes. And so I'm just going through a little bit of the background here. In the past, one of the ways we've tried calculating the basin volume is calculate the Hessian, which is to do a second order approximation of the basin's curvature at the bottom. The issue is this is pretty bad for neural networks. This doesn't work for neural networks because your basins don't look like this. This is only an idealized version of what your basins look like. Your basins look like that, or they look like something like that in a high dimensional space. So your basins are really weird. The curvature is flat at the bottom, which means that when you use a Hessian to try and estimate like the volume beneath some bound, you get infinity. So you can't calculate the Hessian, at least not in this naive way. Sparsh.
How do you know what basins are shaped like?
Yeah, so you can sample around them. Like you can take random samples and see the height. So you can, for example, you can take a 3-dimensional cross section, or sorry, I should say a 2-dimensional cross section of your loss landscape, and then plot that cross section. Or you can calculate statistics about the geometrical properties of the loss basin without visualizing it. But it's very hard to visualize, obviously. Yeah. Yeah, I saw a hand for a second, but okay. Yeah, so this doesn't work. We can't just calculate the Hessian and use the Hessian approximation directly. And neural network basins look like this. They look pretty bad, or they look pretty weird. They don't look like these nice bowls. In fact, they look like something like this, like a very cavernous, canyonous basin. And what we notice is that at the bottom of these basins, there is, there's like this level set. There's this like level set of parameters that are all equally good. They all have the same loss. So this seems really weird. Like if we go into these basins, I should say like canyons, there are many directions in which we can go where like our loss literally doesn't change at all. So why is that?
Is that related to like the previous slide? Like you could change one rate and then increase the other, like you could increase one and then decrease the next one. And then that's like a line of solutions. Is that like what we're...
Exactly. Yeah, I think you're perfectly right here. So because neural networks are not injective, that means there are directions in which I can move in parameter space that don't change my function. That means I can like increase this parameter in one dimension, and we can decrease these parameters in the other dimension. And so that leads to a vector direction in which we can move in that doesn't change our function and therefore doesn't change our loss. And then this is not the only way that we can have these level curves. We can also have level curves because in our network there might be a lot of redundancy. So in the network, maybe we have like 5 copies of the same circuit, and then we can maintain performance by increasing and decreasing the weights of the circuit's outputs. So we can say like, I weigh the output of this circuit twice as much as I did before, and then I will downweigh like a remaining circuit. And because I'm redundant, like these two circuits are identical, and we can maintain performance and maintain their function. And so in some sense, our loss landscape is a property of our model's algorithm. By looking at the loss landscape, it tells us something about the internal properties of our model. And essentially like how weird our level set gets is a geometric property of the loss landscape. And it will change during model training because as your model gets less and less redundant, less and less of its weights like implement the same function, it gets less and less weird, basically. Yeah, so I just dropped a pretty heavy concept there. So any questions about that? Yeah, you?
Does this reflect the model of architecture? So the knowledge that humans have. Is it one based on the data set that have this loss landscape or the model of architecture?
Aha, it depends on both. So your loss landscape is a product of your data, but also of your model architecture. So obviously, if you have a model with more parameters, then your loss landscape will be higher dimensional. And your data will structure like the dips in your landscape because they tell you what solutions are optimal. So it's a product of both. Both are important. And if you change your data or you change your model, your loss landscape will not look the same. And so I'll tell you guys why it's called singular learning theory. These functions are singular. Singularities in mathematics refer to points where you can't differentiate or like the derivative is not well defined. And for example, in these basins with flat bottoms, the second derivative is not defined. Or it's zero, like the Hessian is not invertible. And so what I mean by that is that the Hessian's rank is not full. It's not full rank, in which I mean there's directions in which you can move that doesn't change your loss. So this is all kind of the same concept. But yeah, so like because you can't estimate using your Hessian, your model is singular, and singular functions are actually an interesting like field of mathematics. I'm not too familiar with them, but yeah, there's also yeah, okay.
But by like singular, like you can go in any direction from the point. Is that a way to think about it as well?
No, that's not the or like something being singular is a more general term in mathematics. But in the sense of like describing neural networks as singular, this is what we mean by singular. There's many ways in which you can move that doesn't change loss. Cool. So I'll introduce volume and singular models. So what we're interested in is not just the volume. We want to figure out the volume scaling exponent. And what I mean by the volume scaling exponent is as we increase epsilon, so let's say a model is in this basin. And as we increase epsilon, which is like, we can think of as the water line, we want to find out how much area is underneath the water line. And the function, basically in loss basins, singular or non-singular, it basically comes out to something like this. So you can have a pre-approximation of the amount of area beneath the water line as some constant times epsilon to the power of lambda. And lambda is the scaling exponent. So what this means is that if your lambda is very big, your volume scales very slowly. And this seems counterintuitive, but remember the epsilon is less than 1. So like, yeah. Yeah, so as like epsilon increases, then your lambda tells you how broad your basin is. If your lambda is very high, that means your basin is very narrow. If your lambda is very low, it means your basin is very broad. Cool. Any questions about this?
Wait, what is it again? So I'm just a little lost. Yeah.
Okay.
Can you like re-elaborate a little?
Sure. So lambda is how much your volume increases as you raise up the water line.
Okay.
Or how much the area underneath the water increases. And because epsilon approaches 0, so epsilon is less than 1, if lambda is very large, then this scales very slowly.
Okay, so larger lambda means that.
That's a narrow basin.
Okay.
Yeah, so like that means that the walls close in very tightly. But if lambda is very small, that means the walls are very shallow. Sparsh?
So generally, do we prefer shallow walls when we're looking for minima in our loss landscape?
Well, let's say you're a machine learning model and you're traversing the loss landscape. are you more likely to fall into a broad basin or a shallow one? Or like a broad basin or a sharp one, I should say. A broad one. So broad basins are, in some sense, they correspond to algorithms that are easier to learn.
And also easier to learn means you're not, well, like wider would mean you're not overfitting.
Because you can shift the loss landscape and it would stay robust.
I guess that was the other point I was wondering about. If you have a very sharp basin, is it more likely to be an artifact of your training data as opposed to something that exists in the overall distribution?
Yeah, this is true. If your data set is limited, or like you have few examples of something, you will probably create like a very sharp divot.
I mean, it's not like overfitting, like literally it's very narrow, like any little change in the weights, you get lost, meaning that you probably just like memorize an example exactly. If you try changing or different inputs, it's gonna.
Yeah, exactly. So like very narrow basins are not robust to changes. So that means if you change your model's weights even a little bit, you can really demolish the model's performance. So as our team said, if you memorize something that maybe corresponds to like a very specific piece of knowledge inside your weights, and then if you modify your weights, then you're not going to be able to recall that knowledge with 100% accuracy, and then you're going to be worse. But if you have some like very general algorithm, maybe it's very robust to damage in the sense of like, if I move my weights around a lot, maybe like the internal like weighting inside my algorithm will change. But in general, I'm still doing something like an induction task. So it's less important.
So do we want a large or small learning coefficient to get like, let's say wider, or we want more general?
This is not something we can directly control really. So it's kind of a metric that tells us something. But in general, having a low learning coefficient is a good indicator that your model is implementing a general function. But obviously, like functions need to have some baseline complexity. Like even if you're doing something like even if you're doing the thing you're supposed to do, like a generalized circuit, you will still destroy it if you perturb it enough. So if your learning coefficient is too low, then that also could mean that like your model hasn't started learning yet, aka it's not in the bottom of the basin at all.
Treating like the whole loss landscape as a single.
Well, we treat the local area around the model's current parameter as the basin, so to speak. Cool. So let me extend this to general like singular models. So for regular models, where the function is injective and it's the loss landscape is convex, lambda is just the dimension of the model divided by 2. But we'll see in neural networks or singular models, the learning coefficient is much lower. So what this means is that standard statistical models, like the polynomial regression I showed you guys a while ago, basically all possible parameterizations of that model are roughly like equally complex. But for a neural network, your complexity can change as you learn. Like how robust you are to damage can change as you learn. So yeah, so it turns out that in neural networks, d/2 forms an upper bound for the volume scaling coefficient. And in reality, the local learning coefficient is usually very, very low compared to how large your model is. So like d/2 for 1.5 trillion would be something like 750 billion. But in reality, your local learning coefficient, I'm just throwing numbers out. Actually, I don't think we have a good calculation for, like we can only estimate it, but it's probably on the order of like thousands to millions. It's not billions. Cool. So yeah, so I want to generate this intuition that like the more weird your loss basin is, aka the more ways you can travel, the more directions in which you can travel and maintain loss, the more big your basin is. So if you have like a really, really warpy basin, there's a lot of volume in the folds. We can just imagine that like this, because of like these channels, this valley-like basin has more volume than like just a regular oval basin. And this is a quote from Jesse Hookland: "There's exponentially more volume in the immediate vicinity of degenerate critical points than in the vicinity of non-degenerate critical points." So that means the more degenerate, aka degeneracy is whoops, not again. Degeneracy is a metric of how warpy or like how many directions you can move without changing your loss. If you have a basin that's more degenerate, that means you have more volume. John?
Yeah. Just to clarify,
What? Oh, D is the number of parameters you have. So the dimension of your loss landscape minus the loss axis.
Oh.
Yeah.
Are you assuming like those go for like infinity though? Like it's not like the lines technically keep going?
Yeah, they don't go for infinity.
Oh, they don't.
No, but
Like taper, they know that taper like.
actually what we find is are there's like kind of like an interconnected network of like paths that you can go on that like don't change your loss.
Well, this leads into like other little sections. Like imagine putting these all together as like puzzle pieces, kind of. Is that a way or no?
Kind of, but we're not worried about that because we never actually travel into these channels. We actually always travel perpendicular to these channels. So in this, I mean, this is 3 dimensions, so it's hard to show this. But normally what happens is this is a cross section of our higher dimensional loss landscape. We're always traveling perpendicular to this because we don't have a gradient in the areas where the loss stays the same. So what this looks like, if you were to visualize this, your loss landscape would warp as you were training because you always move in direction perpendicular to this set.
Yeah, because like when we're doing training, we're not moving in the direction with 0 loss change. We want to move in the direction with loss change. So we wouldn't
Exactly.
move along any channel that's not changing unless we move like.
Yeah,
down.
perpendicular.
Yeah.
So actually, I gave you guys a wrong idea the last time I did the SLT talk. I said that they would like bounce around the channels. This is not actually true. But yeah, so what this I mean, I guess like intuition is that like if you were to plot the axes where your loss doesn't change, you would see like you would start in training like seeing like these like very complex folds, and then as your training continues, you would move perpendicular to this, and you would see your loss landscape kind of simplify itself. And then
do you mean like so your loss landscape doesn't actually change, but it's just like what you.
no, just a local slice around you. Yeah. Yeah. So something I want to say is that the foldiness actually dominates the volume even more than the size of the basin. So if your small basin is more foldy, it's actually more volumetric than a large basin that is less foldy. Yeah, because like lambda is like the exponent, whereas epsilon is just like the thing taken to the exponent. Like for example, if you have a basin with local learning coefficient 25, then 0.01 to 25 is like immensely larger than 0.01 to the power of 50, right? If you had another basin that had a local learning coefficient of 50. So more foldy basin. Yeah, more foldy basin means lower LLC. More foldy basin, way bigger than less foldy basin.
So that'd be 25 enough.
No, because it's less than 1.
No, like,
Right.
Except 25.
Oh yeah, so this is 10 to the power 25. Yeah. No, it's 50 because it's 0.01, not 0.1. Yeah. And remember that epsilon approaches 0. So 0.01 is way larger than epsilon. Yeah.
Where do you get 25 and 50 from?
This is
Those
an,
numbers.
this is just an example. So like, let's say we had 2 loss basins, one with a local learning coefficient of 25. And remember that local learning coefficient is also the scaling exponent. So this is like a very not foldy basin with a scaling exponent 25 versus, no, sorry, this is very foldy versus very not foldy. So it's easy to get this mixed up.
Oh, okay.
Yeah.
So narrower basins are more folded.
No, more foldy means more broad.
Oh, right, okay.
Yeah. Cool. This is definitely a confusing concept, and I hope that the I had some like visualizations and exercises on the next pages that might clarify some of these ideas. So let's hold questions until afterwards. Cool. So this is the distinction between injective models, which are like statistical models, and then singular models. So if you were to fit like some kind of polynomial fits, then you have like one optima in like a broad wasteland. Like all these, there's only one good base, or like there's only one optima because every function maps, or every parameter maps to like a different function. So there's one optimal function, which means unless you're well, I guess depending on your loss function, but yeah, generally there's like a single set of parameters that like implements the optimal function, because
So like in a polynomial, it's because the one parameter can only control like the x squared, one parameter can only control the x cubed.
yes,
Whereas in a neural network, a single parameter or multiple parameters could create their own X cubes.
Exactly.
themselves.
Multiple parameters can be simplified to one parameter, basically. If you have multiple redundant copies of the same circuit, then you can view them as just one circuit.
Versus polynomial, it's like each weight can only control its own thing.
Yeah, or like every function needs to have its unique set of parameters, unique parameter. So if there's only one optimal function, then there can be only one optimal weight. But in neural networks, if there's one optimal function, there could be a set of weights, like the level curve, that implement the optimal function. Yeah, so why does ML work so well? Kind of. Singular models, there's many easy to find decent solutions. Whereas for injective models, it's pretty hard to find optimal solution. Or it might be easy to find, or like this optimal solution might be very narrow or something like that. So yeah, so here's some examples, some exercises. So here are two pictures. Actually, this is okay. So this is a bad picture because this isn't a lost landscape. This is actually a model distribution. So ignore this. Pretend as if these were flips. So which one has greater volume if we flip these like upside down?
Wait, which are we looking at
The left one.
Gray, the gray?
The gray, yeah.
Both the grades are we comparing?
Yeah.
The right.
Keep flipped up upside down.
Yeah, because these are not lost bases because they go up.
That
Okay, we can-
that one, the one on the
the
right.
thing
Okay. Yeah.
discuss with our partners.
Okay.
Wait a second.
Do you guys want to? Actually, okay. So I'll go straight to it. So it's the one on the right. It's easier to follow to the one on the right than the one on the left. And then number two. Okay, I want you guys to actually discuss with your neighbors for this one. Let's say you are a random walker and you are walking on this like level set. Where are you most likely to be? Okay, yeah, take 2 minutes to discuss.
Are we on the right? Are we saying on the right image?
On the right image,
On the
yeah.
right image, if we're walking around.
Which-
on the like black lines.
On the black line, yeah.
So we're wandering around on the plane and the question is like, which elevation are we most likely to be in?
No, we're walking around on this graph. So we're a random walker, we're a point on this graph. And we can travel, on the line.
Basically, like, imagine like, if you guys are robotics in high school, you're like, oh, you wrote that stupid line following robot. And it's like really dumb. So you're following the line and basically at some point, I don't know, William checks his watch and be like, okay, we're checking where you are right now. Where are you looking?
Yeah. I think most of the time, every point has equal probability. You're gonna come back to the center point. Right, and then you're gonna do it at any other one. So then you're always, the center point, you're always gonna come back to right one. So like you're most likely to be at a point where you have a lot of, whoa, that's weird. You're most likely to be at a point where you have a lot of options. Well, because there's a lot of options to come back to. That's weird. So it's like you're like talking. That's true. I would talk about. I'll raise my hand first. You're gonna lose. So.
I'm gonna ignore you, kid.
No. I'll do my I'll do my discussion. Percent extra. Yeah. So, yeah, is that always the case or no? So that's my question. Always the case. You're most likely to be at a point where you're at a single, like most of the time you're at a single.
All right. So since the discussion is winding down, I kind of want to hear from like 2 or more different groups, I guess, about what their thoughts are. So
Volunteers.
yeah, any volunteers that isn't our TA. Yes? Oh, sorry, what's your name?
I'm Kartik. I
Kartik?
think it's the center point because if you're doing a random walk, you're gonna end up at the spot that's most likely to be seated. So the way I thought about it is marbles in a bag, where you're gonna be 4 center swing marbles in a bag. Less than 1 marble. If that makes sense.
Like marbles in the, like you shake around marbles in the bag?
Yeah, kind of. I basically assigned each point around marble, and the center point is 4 marbles.
Oh, yeah, I see what you mean. That makes sense. Yeah. Yeah, so like there are definitely, spots of higher probability and lower probability. And yeah, Sparsh, looks like you guys were talking for a while.
Oh, yeah, we were talking about,
Okay.
About the channels and like why they'd be more common in like higher dimensional space.
Oh, gotcha. Yeah. I mean, if there, so actually in higher dimensional space, there are more channels because there are fewer basins and there's more saddle points because it seems very unlikely that you are at a spot where all the walls, walls rise around you in every dimension. So in 3 dimensions, or in 2 dimensions, you can think of like basins as being extremely likely. In 3 dimensions, you have saddle points. You could be a saddle point or a basin. In higher dimensions, you're almost always at a saddle point. So actually, there's a study of machine learning models as saddle to saddle transitions. So you transition between saddle points of different complexity. So it's very similar to SLT actually.
So you're saying like you have base, if you pick the right dimensions, you're always going to be at a basin with respect to those. Is that what you're?
Yeah, exactly. John?
So I guess on for the figure like on the left, right? Or let's say you have like I don't know like some like network like would both of those be considered basins? Like either of them.
Oh, yeah. So actually, the way we think of basins in SLT is somewhere where your model's loss is like moderately low, and it is moderately hard to increase your loss. So this like technically there's only one, or there's like probably only one optimal basin. Like there's like one global optima, but we consider like any local optima or like a saddle point as a basin as well. So like the same neural network when traveling or when being optimized can look at its surroundings and see this basin, and then maybe also see that basin, the other basin at a different time during training. Hope that answers your question. You still look a little bit confused.
Oh, no, I was thinking because I was trying to I've been trying to wrap my head around like how the best thing works. So like what is it okay, I'm trying to check my understanding. So like let's say you had like a low lambda. Does that mean that there's like only let's say like lambda was 2, does that mean that there's like only 2 directions you're going where like you're actually like significantly decreasing your cost, and other like directions where like basically it's like you're like going.
No, actually. So recall, what does lambda refer to mathematically? It's
It's the learning, those learning factors.
It's the volume scaling exponent.
Yeah.
So if your volume scaling exponent is very small, that means that your basin is that means your basin is very broad. Because you take a small number to the power of 2 as opposed to the power of like 50 or something.
Oh, I see.
Cool. So yeah, actually the local learning coefficient is like just it's just your local scaling exponents, but empirically it also like corresponds to foldiness. Yes.
About this random walker question.
Yeah.
What are the lines supposed to represent? Because we're not traversing through the basins.
Right. Yeah, so that's a good question. So we're not traversing through the basin, that's for sure. So like generally when we look at this, our model is at the center, and we can just see the level of sets around us. But it just means that like let's say our model wasn't at that point and it was elsewhere. It is that you also have like some minimal movement along the zero loss channels because of batch noise. So in your full data set, the gradient in these directions is 0. But because you're taking mini batches, there is some noise to your gradient. So you actually are taking like a slow kind of random walk inside these dimensions. But yeah, if you were to visualize your full batch like loss landscape, like at every step, you would move perpendiculars. You would move like mostly perpendicular to these.
Although if there's noise in the batch, which causes like how do we know that it won't like stay in the same spot?
Yeah, so your model doesn't stay in the same spot during training. But if you mean relative to this level set, yeah, your model will walk around the level set slowly. But as we've seen here, it's more probable for it to be kind of at like the center junction point. And empirically, this is what we see as well.
Well, can you always just wherever you are, like you brought the blue point, I could just look at some other dimensions and be at that center junction point? Like,
yeah, you can
always
as well.
just pick a center junction point with respect to some dimensions.
Yeah, actually, yeah, I guess in that case, like I wouldn't, or I guess maybe this is just the intuition building thing. Because yeah, I'm actually not sure how to think about this. Because it is true that like this is just like a cross section. You're um it but it is true that when you look at your parameter at every point in its training, it is very likely to be at like a junction point. So maybe there's like some equivalence between like being at a junction points, or you know, it is possible that like your model exists in places where there's like very few junctions, but there's like less volume in those areas or something. Yeah, I guess this doesn't work too well as intuition pod. Thanks for pointing that out. Yeah, John?
So sorry, I'm still like a little bit.
Yeah.
Okay, so like, let's just look at I guess the two examples, right? So in my mind, like the left hand would have like a lambda of 3 and the right hand side would have a lambda of 6.
Yes.
But then if we're zooming in those, right? So with lambda of 3, there's sort of 3 directions that we could go down.
No, it doesn't mean that. It doesn't mean that there are 3 directions. So the number of like in the 3 directions does not correspond to your local learning coefficient. Like your local learning coefficient is related to like the number of directions in which you can go, but like it's not an equivalence. Okay, yeah, actually I'm not too clear on this as well. So that's a good question. I do think like the research is probably fairly novel. So if you guys actually want to ask the people who produce this research, I think they're pretty approachable. So yeah, although it is being investigated as well. So I'll talk a little bit more about that in the future. Okay, so let's talk about like the effective Occam's razor. So like, what does this mean? And why do like machine learning models work so well? Why do they not overfit until you train them on the same data like for 100 epochs, or I guess more than like 5 epochs? Well, the idea is Occam's razor. Simpler solutions, like algorithmically simpler solutions, are easier to find. And what I mean by this is that the more simple your algorithm, the more fully it is. Why is that? Because you can be very redundant when implementing a simple algorithm. Let's say your model has like 1.5 trillion parameters, but it's implementing like an algorithm that only requires like 100 million parameters to implement, and just has like many copies of that same algorithm internally, like many different copies of the same circuit. In that case, it's very redundant. That means there's a lot of redundancy, and there's a lot of ways in which you could travel and not change the weights, which means it's very likely for that position in loss basin for a model to fall into it. So it means you're very likely actually early on in training to have very many redundant copies of the same circuit inside your transformer. You're very likely to actually like implement something that could be implemented with a simpler neural network, if that makes sense. So effectively, your neural network is emulating a smaller one. It's using like 10% of its brain power, like early on. And then that increases through training. Yeah, you?
A large amount of possible circuits that so is that
why? If I'm correct, are you talking about developmental stages, like critical periods, where like if your model is trained on English, then it has a harder time learning Spanish than if it was trained on Spanish?
What I mean is that as you increase the number of parameters,
yeah,
the chance of increase up until a certain threshold, and past that threshold, the model starts to generalize as well.
Ah, the double descent. Yes, exactly. This is exactly what I'm talking about. So after a certain threshold, your model becomes very singular. Or, well, okay, so I should say this. So let's say you're training a small model on a task, right? Let's say the task complexity like approaches the model's complexity. That means like the general circuit is sufficiently complex that like the model would have to use like all of its weights in a non-redundant fashion in order to implement it. This is really hard to discover. It's really hard for a model to learn something that requires very low redundancy in it. Like you can kind of think of the model as like if it were totally non-redundant, then the basin would not be singular at all. Well, the basin would be like convex. So it's like really hard for your small model to learn a function that it is technically capable of learning. But if you train a large neural network, then it can learn that function really easily. It can learn a simpler function And it might only use 40% of its parameter counts, but it will learn it pretty well. And this is why you can do like pruning, which is you train a large neural network to perform some task that it's over parameterized for. You train it, it learns it fairly easily, and then you prune away the extra neurons that are unnecessary, and you can prune pretty significantly, unless your model is very, very overtrained, which is what is true for llama, for example.
Wait, so like, okay.
Yeah. Yes, Marsh?
I'm still not seeing why this would prevent overfitting.
Right. Because it's Occam's razor. Simpler solutions are more likely to find. So your model can overfit. But let's say you're starting your training with a large model, and you have like complex algorithms and you have simple algorithms, right? And your model can fall into these basins. It is way more likely for it to fall into a basin implementing a simpler algorithm first, because the simpler algorithms have bigger basins.
Oh, I see, because they have the simpler algorithms have more redundant parameters.
Exactly.
Is that also like if you have a large model and smaller data, that literally is a quote unquote simpler like problem or like simpler?
Not necessarily. No, if you have less data, but like the data is drawn from the same distribution, it doesn't change it just means you have less optimizing steps, assuming you don't run for multiple epochs. Yes.
What do you mean by large model, number of parameters or the
Number of parameters. Cool. So yeah, so what does training look like then? Well, when I was talking about saddle to saddle transitions, we have, like if you plot out the basins around it, you have basin to basin transitions where you start off with like this very degenerate basin, very warpy basin, and you go into these increasingly narrow basins that implement more specific algorithms. And so actually we find that it's very, so like as the loss gets lower, like as we continue training the model, then we kind of force it to go into lower and lower basins because we put pressure on it to decrease its loss. We travel with regards to the gradient. And eventually we can overcome our simplicity prior to reach more complex algorithms. Yes?
Just for clarification, you mean simpler as in like number of, I guess, redundant weights per se?
Yeah, so like a simple algorithm is something that can be implemented with few weights. So if you have many weights, you can implement it very redundantly. You can essentially implement it with weights to spare, so to speak. But if it's very complex, then you would have to use a lot of weights to implement it, and you can't spare the redundancy. You can't afford to be redundant. So like your model transitions from these like higher, simpler algorithms. So generally, I mean, this is not always true, depending on your data. There might be an optimal solution that's pretty simple if your task is simple. But let's say your data is something like language model. Well, then you have some simple solutions, like you just memorize like the letter frequencies. That's very simple, very easy to do. You can do it with like huge amount of redundancy. But then there are better solutions that do things like bigram modeling or trigram modeling. And then there are even more complex solutions that rely on things like induction and reasoning. And so we see kind of like these phase transitions in models where they drop from these very easy to fall into broad basins into these narrower basins that implement better algorithms that are more complex. So as I said, it's not always that more complex algorithms are better, but if you're training it on a task that can be pretty complex, then in general, like for language modeling, more complex algorithms do end up being better in terms of performance. So yeah, so you're kind of always like in the struggle between simplicity and like algorithmic complexity, like loss. So you can put more pressure to select more specific algorithms by training it more, basically. Yeah, Sparsh?
How does this relate to the idea that in neural networks, earlier layers learn more general features and later layers learn more specific ones?
I'm not sure it does, or I think it's just necessary to do some general data processing before you can do the more specific data processing. In sense of like you need to figure out which verbs are referring to which nouns before you can process like who's doing what, for example. John?
Yeah, so okay, so I guess like I'm trying to check if this is a good way to think about it. So the lambda corresponds to like sort of like number of affected parameters as so it says if you have like you have a base and then all the other dimensions are then forming a singularity line, singularity contour. So then those could be then be replaced by constants, right? Like
Oh,
You like prune them, you're saying? You can get rid of those weights? Is that what you're-
Yeah, you can replace them, because you can just replace them with constant instead of variables as your.
right, like you don't have to,
You're fixed at that dimension, right, because you're moving on that line.
right.
Okay.
Yes, yeah, actually, there is a strong correlation between local learning coefficient and effective parameter count. So as your local learning coefficient increases, so does your effective parameter count, like the non-redundant parameter count.
Yeah, of course.
So yeah, you're perfectly correct. And so this is a diagram of, if you were to plot out the level curves around your model as it trains, then you will see that as your model gets more and more complex, then this thing gets less and less weird, less and less degenerate. And yeah, so at the start of training, your model is very, very degenerate. We can calculate this number and we can tell you that it's very low. Not the degeneracy. The degeneracy is very high, but the learning coefficient is low. Lambda is low. And then lambda increases. And yeah, so this is how your model performs during training. And lambda is something we can estimate in order to give you a metric. And it turns out, over the past few months, there's also been a lot of research done to use lambda for many other things as well. So it actually has quite a lot of additional utility behind being a metric. Okay, so here's the idea. So if you guys are physicists, actually, are there any of you who are physicists? We don't have a single physicist here. Okay. But okay, so in physics and also I think in biology, I'm not sure, there's like this idea of free energy. And so we're actually optimizing this free energy. We can kind of think of this optimization problem as not just a loss optimization problem, but as a free energy optimization problem. So this is the WBSC, or the widely applicable Bayesian information criterion. It's a mouthful. Is your loss plus lambda log n, and n is the number of training samples you have. And so we can make this mathematical statements given like a very specific case, like if we're doing Bayesian optimization instead of SGD. But in reality, like empirically, this also kind of holds up. So we're kind of at the start of our training, our complexity is very low, but our inaccuracy is very high. And so as n increases, as the number of data points we train on increases, then there's more pressure towards decreasing inaccuracy and less pressure towards decreasing complexity. And as n tends towards infinity, then this term multiplied by n dominates this term, which is multiplied by log n. So that means if you were to train for an almost infinite amount of time, then you would only be interested in finding out the optimal loss, and you wouldn't care about complexity. It would be of no cost to you. But modern models, obviously, you have a limited amount of compute, and so you are somewhere on this balance. If you don't train at all, well, then you have very low complexity, and like you have very low accuracy. If you train a lot, then you have high accuracy, high complexity. Yeah.
It's just training.
Exactly. Cool. So I just threw out a lot of terms, and so here's a cheat sheet. I think this is primarily for the benefit of if you want to like look at this afterwards. But yeah, so once again, neural networks, they're singular and they're non-injective. More degenerations means they're more folding, and it means there's more volume, and it means there's lower learning coefficient. So if there's more degenerate, they're less complex, lower local learning coefficient. And so you have this equivalence. So if you have higher LLC, you have a more complex basin, you have a less degenerate basin, and you have less volume. So higher LLC, small basin. Low LLC, big basin. Probably bad algorithm. Cool, doesn't make sense. This is like the core idea behind SLT. Okay, and so I didn't talk about this last time, but how do we actually calculate lambda? Like empirically, like we can do all this math on some like idealized function, but your function is like we can only estimate it empirically. And how do we do that? So here, let me just talk about Bayesian learning real quick. I know your eyes are probably glazing over, but I'm sure you guys are familiar with Bayesian statistics. I'm sure you guys love it. Yeah. Does anyone want me to talk about what Bayes' theorem is? Does anyone not like, or I can kind of go over it very quickly. Yes. Okay. Sounds good. Okay, so Bayes' theorem is a way to update, like if you have a probability distribution and you find some evidence, how do you update your probability distribution? So let's say you have like a one-dimensional distribution over your belief of, is it going to rain today? You can like transform the distribution if you hear your friend say, oh, it's probably not going to rain today. And you know that your friend is probably like 80% reliable. So 80% of the time, in which case he says it won't rain, and 20% of the time it will rain. And so you can use Bayes' law, which is a pretty simple mathematical like formula to update it. I don't have a slide here, but you can search up Bayes' law. But the core idea is that in machine, like we can treat stochastic gradient descent as similar to Bayesian updating. So we initialize our model's weights over a Gaussian. We do like Saver initialization, and our weights are distributed like this. And then as we train it, our weights get localized. Our weights get more and more centered at those locations in which they have good loss, they have low loss. So we can treat this like essentially instead of like picking like one spot to start with and then using SGD to optimize. Here, like as an idealized mathematical framework, we take the whole distribution of where it's likely to start and then do a transformation on that to figure out where it's likely to end up after you've optimized it. So you have like some posterior distribution that you can calculate using Bayesian learning. And there's this paper called Stochastic Gradient Descent as Approximate Bayesian Inference that shows an equivalence. Like it's like basically the distribution, like if you did SGD many, many times, effectively your distribution would be like some tempered version of the Bayesian posterior. If you knew if you could somehow update your, if you could do like optimal Bayesian updating on your model's initial weights. Cool. So this is a handful. I don't know if this is interesting to you, but I will talk about it anyway, because it's very cool. Okay, and so this expression is the one we're interested in. Lambda hat is like empirically what our local learning coefficient is, and it's the expected value of the loss minus the loss at the optimal points. And so what does this mean? So we can think of W as being the model posterior. So the distribution over the weights is likely to end up being. And if we can sample this distribution, then we can calculate the average loss of this distribution subtracted by the loss of the optimal points. And then divided by log n, where n is the number of data points. And then that is our lambda hat. And so it turns out empirically you can actually do this. I'm gonna skip over this because this is more math, but the idea is you start at you train your model, or you freeze at some point in training, your model's parameters is over here, it's somewhere inside this loss basin. What you do is you do SGD, so you continue going down, but you add noise to wiggle around. And then if you take a bunch of samples during this wiggling process, then you can sample from the Bayesian posterior. There's something that shows you that if you do this process for infinity steps, the stationary distribution is equivalent to the posterior distribution.
So it's pretty much to calculate the expected value, you just sample around your point. Is that a simple way of saying that?
Yeah, exactly.
Okay.
Yeah. And so the idea is if your basin is very narrow, aka the LC is very high, then if you do some wiggling, then you're likely to wiggle up the hills a little bit because it's so narrow. So your average loss is going to be a little bit higher inside this distribution. But if your basin is very broad, then you can do a lot of wiggling and not actually raise your loss a lot. Yeah.
And this W star is on the result after you continue the stochastic gradient descent until you reach the bottom of the basin.
Yeah, or in practice, W star is your current model position.
I would just where you start when you cut the point where you find the
LLC.
Yeah. So it's like you're training, you're at a point, I want to know my LLC.
Yep.
That's my W star, the point I'm at in training, and I sample around it, and then I figure out how much the change was, and I calculate the learning coefficient, and then I train later on.
Yep.
And I'm at the point that's W star, sample around it, figure out learning coefficient in that area that I just moved to, and then you can see the learning coefficient change as you move. Okay.
Exactly. And this leads this is not mathematically rigorous and leads to some weird things happening. For example, if you try to estimate your LLC at the start of training, your LLC will be negative because the SGD part of SGLE will cause your model to go more down. So the expected value of under this sampling is lower than your model starting position. But if your model is in the middle of its training and it has learned some algorithms, then usually this LLC makes sense, or it's like a good estimation in some way. For you?
Like you said, outbound sort of
Yeah.
That like think about it.
Exactly. Yeah. And you can't, like, the idea is, what if you could just calculate the Hessian? Well, you can't. You can't calculate you can't estimate the curvature by calculating the Hessian because I'll say that the curvature is 0. Anyway, cool. Yeah. So like this is SGLD. You do wiggling around using random noise. So the question is, does this work? And the actual answer is yes. So yeah, so this is a GLA. So we can estimate the local learning coefficient of any neural network. We have a GitHub for that. You can download my code. Partly my code. Anyway, this is for a deep linear network. So this is like a very simplified type of neural network, but it is a type of neural network in which we can calculate the true learning coefficient. And we see that the estimated local learning coefficient is linear with the true learning coefficient. And you see they actually hit at the grid points. So the estimated local learning coefficient is actually basically.
How do you know the true learning coefficient?
Because this is a deep linear network and you can factor it into a single matrix.
But if it isn't a linear, let's say it's a natural number, like activation.
We couldn't calculate this true value.
Yeah.
So this is like a, like a sanity check. Like this is,
Okay.
does our estimation match up with the real
For
values?
absolute networks, you have to do the estimation. That's the whole point. You do sampling.
Exactly. We can't calculate the true learning coefficient for any neural networks that are interesting. But yeah, so like, this makes sense. So this is a model. I believe this is also a deep linear network. But this is also true for models that are not deep linear networks. I can attest. So like for transformers, you will also see these increases in learning coefficient when your loss drops. So in neural network training, you often see these phase transitions, and it's true that these phase transitions correspond to corresponding phase transitions in the local learning coefficient. So your local learning coefficient can be like a good alarm in some sense. It sometimes changes earlier than your loss because your model is developing these circuits, but it hasn't uploaded them and used them in its output. So your local learning coefficient can increase before your loss decreases. So it can be like a good early warning signal. Yes, Parsh?
So maybe a way to think of it would be that as our local learning coefficient, you said increases, that would be our model is like start to circle around a narrow basin.
Exactly.
Sort of go into the narrow basin, you have to decrease the step, otherwise you like skip over it.
Yeah, so that's why you have to lower your learning rate. And often when you lower your learning rate, your loss immediately drops soon after, right? Yeah. Do you?
So like the graph on the right? What you're doing is based off training at a certain point, really randomly sample around that stick loss, and then they calculate the value.
Yep.
So that's the way we're doing it.
Yes.
And so can you technically, if this does work, use that as your loss and just optimize for that?
You can't calculate the gradient with respect to it.
It's a little hacky though. Like, okay, I did a predictor of loss by having this value as LLC, which is I sampled around my loss. Of course, it's going to be correlated with my loss and show, won't it? Like, how does saying like you're like, oh, loss drops and my other new amazing metric drops, but that metric is just like
no,
it even includes the loss and it's samples around it. Like
I know, but in some like this metric is predictive in some like not all the time, but some of the time it rises before your loss drops.
Oh, well, because if you sampled around it, you can see you're more likely to.
Exactly. Yeah. Okay.
You look ahead and
okay. So
what is this? What is this? What's the use of what's the...
Okay. Let me okay. I forgot to put Gronk here. Or okay, that's not Gronk, is it? What's this guy's name?
Gronk is the main guy. That's like the
That's Pacha, I think.
Oh, okay. Sprite down. Sprite, you have a good memory. Okay, I'll talk about some of the more useful applications for of this. I forgot to put, okay. I remember to put this here, but I randomized which slide I put it on, so I didn't know where it would be. But here's our team with Boba, jump scare.
Thank you.
I thought you guys would be like falling asleep by now, so okay. Cool. So going back, our machine learning models are these big calls of linear algebra. And maybe we can reason about this big pile of linear algebra, not by looking at the linear algebra itself, which is what Mechantrip is doing, but by figuring out how the linear algebra is influenced by our data. So actually, maybe what we should be thinking about is more about like some metrics we can calculate using the loss landscape. So here's an interesting part. So we can figure out how models develop. It's called the developmental trajectory / the developmental landscape. And I don't know if anyone here is a bio major, but I'm told that in biology or in cell development, there's a similar landscape that you can kind of draw with like energy levels. And cells start from being like pluripotent cells and differentiate into more and more specialized cells. And so they're kind of like flowing down this mountain. It is like possible with like certain factors to change the landscape, like signaling factors, to cause maybe these specialized cells to become pluripotent again. And just like Yamanaka factors. And here's the thing, we can kind of do the same thing with neural networks, or neural networks also undergo some similar patterns. Like children, neural networks have critical periods. For example, for language acquisition, like if you as a kid don't learn language, then it'll be immensely harder for you to pick up linguistics later on. This is the same for things like three-dimensional visualization. So if you go back like to ancient art, one of the reasons they had such poor perspective is because it was not something that was practiced, and therefore it's like harder for artists to conceptualize / learn. But yeah, so like neural networks likewise also have things like modal composition. If you have a neural network that's very good at predicting text, and you start training it on images, then it will be worse at images than the neural network that's trained on text and images from the very beginning. So this seems fairly important. And what can we learn about it by looking at the loss landscape as the model learns? Well, let me play this video. Here's a development of a 2-layer attention-only language transformer. Let me explain what these metrics are. Okay, so this means nothing right now. This is the local learning coefficient. So you can see it's going up, some goes down. And that is the model's position in the loss landscape, or more specifically, a PCA of its position in the loss landscape. And these are 3 different views of this like line moving in 3-dimensional space. So these are like 3 different cross sections of our 3 PCA vectors. So imagine there's this line in 3-dimensional space, and these are 3 windows positioned at 90-degree angles at which you can see the line in. And then what's interesting is we can look at inflection points inside the local learning coefficients at different parts of training. And we noticed that that the model, like this corresponds to the model going towards different attractor points. So for example, in yellow, it's being attracted to this attractor point. But later on, we see it being attracted to another attractor point at another side. So it's actually pretty interesting that like inflection points in the learn coefficients correspond to like transitions in loss, but also transitions in like the attractor points, aka the gradients, for the neural network.
But could you explain that part about that attractor points again?
Yeah, sure. So if you look at these circles, perhaps the circle is better to look at. This is the attractor point. So it's like if you take the curvature of this line trajectory now, you can kind of figure out like which point is pulling on it gravitationally. You can think about it as like that. And so if it's so you see in this attractor points, will form right here, the circle is being attracted towards.
What are the colors?
The colors are they're just colored by different phases in the local learning coefficient. And so we just chunk these into phases based on their inflection point. So you see this inflection point, we mark this as an arbitrary delineated.
Yep.
So, I mean, lost landscape wise, it's like you have those basins and maybe you're veering towards it, but then there's a stronger one, you just keep.
No, it's like you fall into a basin and now like the direction you're pulled towards changes because you're in a different basin with different dynamics.
Oh, it's the like dropping.
Yeah.
Thing.
Yeah. So yeah, this is cool. Whoopsies. Okay. It turns out that these developmental phases are interpretable. So through a variety of handcrafted, so like the progression of a standard 2-layer attention-only language model is like this. This is 2 layers, so it can't learn anything more complex than induction heads. But this is what a 2-layer transformer learns. It learns bigrams. It learns various n-grams. It forms because the induction circuit is 2 layers. It forms the first part of it, which is a previous token head. And then it forms the second half of it, which is the induction head. And then it finally converges. which means it like fine tunes its weights a little bit, depending on what tokens are more or less likely. And guess what? These 5 phases correspond almost exactly to these 5 phases.
Whoa.
And so it turns out that like by kind of visualizing the inflection points in your local learning coefficient, or by inspecting its trajectory in the loss landscape and figure out its attractor point, you can kind of determine when your model has gained a new capability.
So like each attractor point is literally like a new phase, like it is literally a phase of development. Like you can
Exactly.
attribute, oh, this point was curving this much towards this, that literally means like it was learning n-gram, and then it's learning like induction head part 1, and then it starts curving and moving towards this direction in weight space. And it literally, that's cool.
Yeah.
That's good.
It's pretty dope.
So I have trouble thinking about it in terms of the attractor points, because like, it's not that there were like 5 attractor points.
No,
The attractor points are like.
so remember that your loss landscape is very high dimensional. This is just a 3D projection. So actually like these attractor points are probably like distinct in, you know, the very high dimensional space, but they get projected down. Like I think that like at times there'll be times in different parts of the learning trajectory. For example, I think here it was attracted to the left, right? And here it's attracted to the left, to the right, I should say. But I think these are different attractor points, where they correspond to attractor points from different bases.
I mean, like, it's like the attractor points here are like moving like very wildly, at least in the PCA diagram. Are they actually moving like wildly in the high dimension space too, or is it just
Possibly.
because then you can't use them as
I
a
I think they're static. The whole point is you're estimating it from the point I'm at, what I think the attractor point it actually is. Like from the diagrams is showing, like you
Oh.
can't visualize that. You have to sample around you.
Oh,
So the
there-
circles are estimations of
Wow.
what I think I'm getting pulled to. That's the second order. That's curvature, right? The approximation of, yeah.
Yeah, I should clarify that these attractor points are calculated from these lines.
Oh, okay, so as you go forward in the line, you just get a better sense of what the attractor point is. And
Yeah.
so there are 5 of them, it's just, these are estimates of what these are at any given point.
Or sometimes you go through 5 different phases. I mean, they could correspond to more than 5 attractor points, but in some sense, these attractor points are qualitatively different. Yeah, so different stages in development correspond to different attractor basins. And then there's like more stuff, but I mean, the animation, I think is more informative. And then I'll talk about the second thing that has come out since last time. So there are weight refined LLCs now. And what does this mean? This means that we can calculate local learning coefficients for more than your whole model. We can calculate it for subparts of your model. Let's say we look at this one attention head in particular, like let's say this like red line. We restrict the weights to that subset. So like, let's say we're only interested in looking at like this subspace of our weight space, or like you look at like this set of dimensions, you look at like a cross section of like a few dimensions that you're interested in, and you wiggle around in those dimensions only. And then you figure out like how tolerant your model is to fluctuations in just those dimensions. And so it turns out that you can calculate different local learning coefficients for different heads, different attention heads. There are these like induction heads that I guess are pretty simple, and the n-gram and skip-gram heads are correspondingly more complex. And it's easy to see why. Actually, the mechanism behind an induction head is, let's say you have a sentence like, Joe Biden spoke at the White House today. And then the token you're trying to predict comes after Joe. So like Joe Biden came to the White House today, Joe, and then you're trying to predict the next token. It's very clear the next token should be Biden, because in your text, there is already a copy of Joe Biden, the bigram. And so what induction heads does is it literally copies the information, Biden should go after Joe, and it copies that to the current position, and it predicts Biden. So induction heads actually are very robust weight-wise. You can scale an induction head, and the behavior will stay, like it's really robust to changes, because the mechanism behind implementing it is very simple. Whereas n-gram heads is you try to memorize n-gram statistics. You're like, oh, I know that like, you know, Cox is likely to follow Joe Biden because Joe Biden likes to talk. I just know this from a training data because I've seen this trigram many times. But the thing is, if you modify those weights quite a bit, then that might destroy your ability to recall that information. And so we can actually classify heads now just by calculating the local loading coefficient of them. We can look at these heads and we're like, these are induction heads. I'm not going to pronounce this. Those are n-gram heads. I don't know why they chose that name. Anyway. Cool. And yeah, so like it turns out that the heads are more algorithmic. They perform a more algorithmic task. They're more simple or more general, some way more robust. and heads that are more responsible for storing information use more memorization. They're less robust, so their local learning coefficient is higher. So
Is it paper or what is this?
this is a paper.
From, is it called Weight Refined LLC?
Search up refining LLCs with something.
Okay.
Yeah. And so yeah, so like as we said, you know, we found that there's like some pretty big distinctions, and the question is how good is this as a classifier? And the answer is it's pretty good. So there's like some pretty clear separation here. You can have like multi-gram heads, and then you can have previous token heads, and then you can have current token heads. So this is development over time. And yeah, so you can see induction heads is like are more simple. Yeah. So this is in layer 0 and this is in layer 1. So induction heads don't exist in layer 0 because they require a previous token head in the previous layer.
This isn't a 2-layer. This is like an actual language model transformer.
No, this is a 2-layer transformer.
Oh,
I mean, we could also calculate it for an actual 7B transformer if you want.
okay.
Like there's nothing stopping us now. Yeah, I saw someone had a question. Okay. Okay, and then it turns out you can also do LLCs on specific tasks. So instead of just like specific heads, you can be like, okay, I trade it on the pile, which is like a big pile of text on the internet. But if we look at a subset of this training data, or we look at some novel data, like data from GitHub, we can see which heads are good at which tasks or are robust at which tasks. So we can see that like, you know, in general, like induction heads there's more simple, but some heads are better at code than others. So yeah, fresh.
Wait, why is the trend flipped for GitHub versus the free training distribution?
That means induction heads are more important for the GitHub task than the training distribution. Because this is looking at the gradient, like this is looking at the loss time state with regards to the GitHub data. So if you think about it, if you break your induction head, or if you vary your induction head a little bit, even though it's really robust, like if you manage to break it, then you will lose dramatic performance on the GitHub task. But if you like, I guess if you like don't remember as much syntax or whatever, it doesn't matter because you can just read the syntax from previous in the context.
What's the distinction then between GitHub and free training distribution?
What's important changes. So what circuits are important changes how much a loss is affected by fluctuations in circuit.
Also, it's not about like how complex the task is, it's about how sensitive the model is to the task being done right.
Yes. Yeah, that's very correct. So in some sense, like your GitHub task is like induction heads are so important for the GitHub task that even though they are more robust in generality, they're sufficiently important as to matter more in terms of the loss. So like if you remember the way we sample the local learning coefficient empirically, so we wiggle around a bit. And so if we wiggle around in the directions in which like the induction heads like if we wiggle around for the induction heads, we might increase our loss more once we reach like the walls, but like maybe there's like more distance between us and the walls or something. But yeah, so actually this is really distinct when we look at the delta. So this is the local learning coefficient minus the pile, normalized by the pile. And so this is kind of the difference between the two. And we can see that induction heads are way more important for code. This seems very reasonable because code is very syntactic and you can copy a lot of syntax from elsewhere. And it looks like there's certain heads that are way more important for the task than others. So those heads are like specifically good for code, but inside a pile, it's not clear that the two heads are different in importance. And so in order to find which circuits are responsible for performance on which tasks, for example, which circuits are good on are necessary for a model to implement math, we can look at the circuits that are very important for the math task. Okay, will affect loss a lot in the math task if it gets destroyed, versus how sensitive your circuit is on the normal task. So if you see a circuit that is like not very important normally, but very important for math, then you know that ablating that circuit will cause your model to, I guess in some sense, unlearn some of its ability for mathematics while not affecting its general performance. So that seems like a pretty interesting thing you can do. So yeah, in terms of the future work, so actually I would like to say that like all of this work, the bundle stages, as well as refined LLCs, this is work that has been done in the past 3.5 months. So the pace of this research is moving pretty quickly. This is still a very novel field. I believe the field is no more than 3 years old. So we still have a lot of future directions in which to go. There's robust RLHF. Once again, maybe there's something we can do to like induce neuroplasticity in these models. Maybe we can somehow allow it to, like right now, RLHF basically just reweights the circuits inside a model. Like the model doesn't really update its circuits in any way. It just learns to use the circuits that end up in more friendly behavior more frequently. But it doesn't really change the structure of its circuits because it's relearned those. And if you were to demolish those circuit structures, you would lose performance. And so maybe there's a way for us to do robust RLHF in which we can somehow increase neuroplasticity and actually change the course of these circuits without impacting performance while making it robustly more helpful to humans, aka robust to distribution shows. Maybe we can also do robust in learning. So as we've said, we can distinguish which heads are important for which tasks. So for unlearning, maybe it's possible to like have a more principled way than just uploading heads that are important for one task and not important for the other ones. Maybe there is some more principled way in which we can do this. So as we said, we can use LLCs as alarm bells. So for example, when your model is developing a new capability, you will be forewarned of it, whether through developmental interpretability or through just like the LLC going up. And you can do automated circuit discovery. At least that's a hope in the future. So the idea is we can find like structures like heads that are important for tasks, but it's still hard for us to find circuits. In MechInterp, we find circuits by looking at the purpose of each component of the circuit and then linking them together, which is a pretty slow, arduous, and human task. It's pretty hard to automate. But maybe there's a way we can get around this. It turns out that weights in the circuit tend to be linked together. Like this makes a lot of sense. But what this means is that you can kind of vary the weights in the circuit in different directions as to not change the whole circuit. So that means if you take a subset, like if you take the weight refined LLC with regards to a whole circuit, that will have a much lower LLC than if you just took any random set of weights of the same size. So what you can kind of do is you can kind of do like binary search on your whole network and then find the weights that are connected to each other in meaningful ways. And those you can just classify circuits. So maybe there's some like efficient algorithm we can do to automatically discover and segment circuits. And yeah, it would make the life of a lot of MechInterp people a lot easier. Sparsh?
I was wondering, you were talking about induction heads and what is it?
N-gram heads?
Yeah, engram heads. So I was just wondering, those are like circuits that we know what they are.
Right.
But by and large, like by far, right, most circuits we would have no idea what they do.
Exactly. We only really know this, we only really understand the circuits in the first few layers of a transformer. In large transformers, we have no idea what the higher level semantic circuits are doing.
So in that case, is this still helpful to analyzing those circuits if we don't know what they do?
Well, right now the thing is we can't even describe which sets of weights are circuits. And so if we can describe which sets of weights are circuits, then there's some automated ways in which we can discover what they do, such as we can turn them off and we can see how the model's performance changes. Okay, so yeah, hope you guys are sufficiently awake after that jump scare. I can go back to it and run it again. Okay, so finally, why do we care about this? I think in general, if we want to build a model, like, so this is a quote by Norbert Wiener of Wiener process fame. Wiener processes are used in like Langevin dynamics and random walks and Brownian motion, so don't laugh at his name, it's actually pretty important. But yeah, so like he said, if we use to achieve our purposes a mechanical agency with whose operation we cannot interfere effectively, we had better be quite sure that the purpose put into the machine is the purpose which we really desire. And what this means is that if we create a strong agent in the future, then it's pretty important that the agent is in some sense aligned or does what we want it to do. Because once models have sufficient agency, then it's pretty hard to course correct them in the sense of a model's an agent has a lot of things that, like, once you are an agent, there's a lot of things that you can do instrumentally that are very good, and you have like instrumental convergence. So one goal an agent might have is, for example, like not being shut off, because if you're shut off, you will not be able to achieve your goal. And it's also fairly difficult to make agents that are corrigible. So for example, let's say you're an AI agent with a specific goal. If someone wants to change your goal, for example, you would score lower on your original goal if your goal was changed. And so in some sense, there's some like innate stubbornness in these, in like general agents when you view them with strong agency and goals. So it's pretty important that we want to understand how these models function and then to create agents that are very helpful to us. because we are in the business of building agents. While current LLMs aren't really agents, even if you build scaffolding, they're pretty weak agents. It's pretty clear we want them to become agents. With O1, for example, it's more agentic, it's capable of doing more long horizon tasks on its own. And general agents are just more useful to the economy, more useful to the companies that want to build them, and more impactful as well. So yeah, what I'm saying is that it looks like models are getting pretty good pretty quickly. And so it's probably good that we do this kind of understanding research sooner rather than later. And I guess there's like common conception that there are barriers that will stop model scaling pretty soon. And here's a report from Epoch AI that shows that's probably not true. In the sense of like, we're not really limited by power constraints. We can use up to 10,000 times more power. We're not really chip constrained. Actually, less than the percent of the world's computing infrastructure currently is used for AI. We're not really that data constrained as well because we have many alternative data sources, and you can always generate synthetic data using things like math. And we're not even constrained by latency, which is just like, as your data centers get larger, you'll need more latency to transmit data between different GPUs to synchronize them. So yeah, it seems like we can probably scale our models by an order, like 5 orders of magnitude or so before we need to start worrying about limits. And 5 orders of magnitude is like GP6 or GP7, which might be quite powerful. So currently we have like ASIC techniques for small models. So we have like passive monitoring. Later on, we'll have active monitoring under AI control techniques. But at some points, we project that there will be models that are sufficiently agentic/intelligent that will be fairly difficult to defend against them in some sense. Like if someone were to ask them to launch a cyber attack and they were to agree, it would be pretty difficult to defend against that or to monitor that or like somehow prevent that in some way. And so maybe it's better that we just build it correctly in the first place. So yeah, so that concludes the talk. This is Jordan, and that's his 4090 and his boba. And he'll be giving a talk in 2 weeks. Is he still here? Hi. Oh, hey, Jordan.
That's week 4. Yes, week 4, Saturday, go give a talk on all things generative vision. Yeah, but let's give a round of applause for Will.
Thank you, guys. Yeah, if you guys have lingering questions, feel free to talk to me afterwards. Let me just check what the time is right now. It's 1:52, so that almost concludes my 2 hours. Yeah, so yeah, feel free to chill. And yeah, I'll be here. I think the cam did pause.
Oh, that's annoying.
But at least it didn't
Audio.
up the screen share.
I'm gonna stop share.
Thank you, Will.
Doing what?
Now I actually have like.
I feel like this one, or I think this one was more accurate. I guess I was. I don't know.
Hey, well, it was a great presentation, you know,
thanks.
I like that, you know, yeah, I want to learn more about it. You have a Discord or something, you have questions that
Yeah, actually, yeah, feel free to, there's a dev interp Discord. I can invite you to the dev interp Discord.
Sure.
You can ask the authors of the paper questions.
So. No, like I'm all the time. So. When you get the math, I can work.
Just the one. Yes. May I ask you what your okay. Can I ask you what your username is on the?
Like I'll go with the math, like the math memorizing and just can't.
Okay, let me try DMing you with the invite link.
Jordan's really good. Jordan's. I know this yours last year.
Oh, yeah.
And I'm so,
I mean, this slide is going to have.
Thank you.
Get more time on the exam, yeah.
So, this happens every.
Yeah.
I think once every 2 Saturdays, I want to say. Next one is Jordan's.
Okay. Gotcha. So, but there's
Like, there's so much new stuff,
Every check
like,
every week.
it would be better. to
There's
just
like
do
a
this one
free
more
session
introductory dinner
I'm actually not sure about
where
this.
I'll do, like full deep dive into
Yeah.
it. There's too much to be able to talk about.
Yeah.
Oh.
About 2 hours.
You'll see, you'll see.
Yeah, that's all
Yeah, we're still using a lot.
Yeah.
Indiana was like, we don't all of it. Yeah. Like, and then, a lot of the new display, first like FPSL for Opus, right? Yeah.
Question over like the.
So it's like that one is like, okay,
Right.
to do one step generation, but still need absolute.
These are confusing
So-
things like
Yeah.
connecting the.
Gaps are not that.
consistency
models involved?
But you can't, so like once.
With the region model?
The consistency model's never really caught on,
Yeah,
rectify
from
flow caught on, but it's still not really one step, there's problems with it.
Is there ways
Like
to
a nice, like,
directive, like,
Yeah.
Yeah, rectify flow and like all the, like, I'm talking like the, I was like.
Carry readers today.
But.
I think it like,
My posture is so bad.
I've got word.
I need to get better posture.
Yeah,
Wondering.
I mean, it's just like a really, really
We
well
don't know the
efficient,
lost landscape. Like the
yeah.
whole point is that we have no idea what it looks like.
That's all it is, I don't know why I call it